This is the second lecture on quantum mechanics. Today we shall discuss about the interpretation of the wave function. In the earlier class we have derived or we have arrived at Schrodinger equation where the time dependent equation is this is time dependent Schrodinger equation in 3D. This describes the motion of a particle of mass m subjected to a conservative force field given by the potential V. This is the Hermitian operator. One thing is that we have arrived at this expression, and we know that psi represents the de Broglie wave or the wave packet associated with the material particle. But till now we do not know how exactly psi is related to the particle behavior. We know only that where the psi will have a large amplitude right on the top of the particle. Now we compare the situation that we encountered in classical physics, especially the elastic wave. We know the elastic wave satisfies this equation. Where v is the velocity of wave propagation and u is known as the amplitude of the wave, which is a real quantity. Actually, even if we represent u by e to the power I k dot r minus omega t as for plane wave, then either the real part of it or imaginary part of it represents the physical field. So in that sense, u is a real quantity, and we know the intensity, that is the energy flux, is proportional to u square. This differential equation is a differential equation involving real coefficients, but it is a differential equation which involves imaginary coefficients as well. So it is logical that psi may be a complex. It is not necessary that psi, the solution of this equation, will be the real one. Keeping this in mind, the role of u square should be taken care of by psi modulus square, where psi modulus square is psi star psi. Now come to the point, what do we mean by energy flux? By energy flux we mean that the amount of energy that crosses per unit area per unit time is the energy flux or the intensity. If we just like to translate this into the particle world, then psi star psi is expected to represent particle flux, that is the number of particles that crosses per unit area per unit time. That is to say, if we have a cylinder whose length is equal to the average velocity of the particle, and if we consider a point over here, then all the particles within this pair will cross this area on probabilistic basis in unit time. So this gives you the particle flux. And since in quantum mechanics it is the probabilistic theory, so the probability will be there. Another way of representing particle flux is multiplying the particle flux by n times v, where n is the number density. So the number of particles within this can be taken care of by n, and v represents the average velocity or drift velocity. Then it is a measure of particle flux. Keeping this in mind, Born came with an interpretation which considers this part only, and he ignored this part, and so he interpreted the wave function he put forward the interpretation of wave function as a representation of the probability density. It is the number density, and the quantum analog of number density will be the position probability density. So as per Born, it is the probability density, that is, it is the probability of finding the particle at point r at time t within a small volume per unit volume. This is known as Born interpretation, and let me write this. So as per Born, rho RT is equal to psi star RT psi of RT. This is the position probability density. So that if we consider rho RT dV, this is psi star RT psi of RT dV. So what does it mean? It represents the probability. If we consider a volume element delta V around the point R, and this, so what is the probability of finding the particle within dV around R is given by this. This is the Born interpretation of wave function. This is an axiom or postulate of quantum mechanics, because nobody knows what exactly psi represents. The axiometric development or these postulates depends on the fact that if we develop theory on this assumption and apply it to the experimentally observed things, if the theory matches with the experimental things, then it is a valid theory. In that sense, it was found that Born interpretation of wave function is most suitable for the development of quantum mechanics. So we accept this as the interpretation of wave function, that is psi star psi gives you the position probability density. One thing, note that we have always written psi star from the left. This is because of the fact that whenever we write the time dependent solution, we write it as like this, and time part, and this part is obtained by the solution of the Hamiltonian operator. We can write it is the Hamiltonian operator, it is a square matrix, so it must be a column vector, so this matrix equation is valid. In that sense, it is a column vector, and psi star is its Hermitian conjugate. So the Hermitian conjugate of a column vector is a row vector, and whenever we multiply a row vector by a column vector, the result is a scalar. Here we are talking about probability, which is a scalar quantity. So that is the spirit of writing psi star from the left. If one writes it in a reverse order, then it will be a column vector on the left and multiplied by a row vector on the right, and the result will be a matrix, square matrix, which represents another operator. We shall come across such operator afterwards. So this is one interpretation. If note the thing, if we consider this is the probability density, then we know from statistics that the total probability is 1. So how to get total probability? If we integrate it over entire volume, then I will get the total probability of finding the particle within the volume V, and that should be 1. This is called the normalization. Normalization of the wave function. Now, since the total probability is 1, we say that the probability is conserved, total probability is conserved. We know that whenever we have a quantity which is conserved one, there exists a differential equation which takes into care this conservation principle, and we know as this one as the equation of continuity. So since the total probability is conserved, one must get a differential equation which takes into account this fact and is known should be known as equation of continuity. We shall come to this part. Let me first consider the special cases of this interpretation in 1 and 2 dimension. If we have a particle system or particle moving in 1 dimension, then the wave function in 1D, the wave function of the particle is psi of xt, and if we consider a point x and a neighboring point x plus delta x, so this is the delta x. So what is the probability of finding the particle within x within x to x plus dx? This is governed by rho of xt dx is equal to psi star xt psi of xt dx. If we have a particle moving on 2D, the wave function in that case will be dependent on two spatial variables and on t, and we talk about rho x y t ds, where the surface area in Cartesian coordinate the surface area is dx dy. If we use polar coordinate, this is dr d theta, and this is psi star x xyt psi of xyt ds. This represents the probability of finding the particle within a area. This is an area element ds. So what is the probability of finding the particle within ds around r at time t? This is the given by this. And the 3-dimensional case we have just described in 3D. The wave function is psi of t, so this takes into account the combination of x, y and z, and rho of t gives you psi star t psi of t dv. So this represents the probability of finding the particle within a small volume dv around r at time t. And what is the normalization condition? The normalization condition here reads as psi star psi dx is equal to 1 over integration is over all x, and in this case the integration, the normalization condition reads as psi star psi ds is equal to 1 all s, and here the normalization condition is psi star psi dv is equal to 1 all v. So all volume is considered. Now I come to the second part, or second another justification of the wave function, that is in terms of equation of continuity or the probability current density. In doing this, we first start with this Schrodinger equation, time dependent Schrodinger equation in 3D. We take the complex conjugate equation of this. So the Hermitian conjugate, the Hermitian conjugate equation of this, which is the obviously function of r and t. We are not writing here. It is a square matrix V psi. This part is a square matrix, and this is a column matrix. So if we take the Hermitian conjugate, it will come down this side, because the thing will be 1 cross n, which is a row, multiplied by this which is Hermitian, so again it is an n by n matrix, and the matrix product is defined. So we write this term as psi star V dagger, where V dagger is the Hermitian conjugate. Since the operator is the Hermitian operator, so this is equal to V operator, and on this side I have minus IH cross del. This is the Hermitian conjugate of this. So if we take the Hermitian conjugate of this is the equation. And let me write this part. I replace H V dagger by V. We multiply the first equation by psi star from the left, and second equation multiply by psi from the right, and take the difference. This term, this will be psi star V psi, and this term will be psi star V is there. When multiplied by psi, it is psi star V psi. When take the difference, these two term goes, provided that V is a real quantity, real function. If V happens to be a complex potential, as people used to use in nuclear physics to represent loss of particles, that is to take into account the radioactivity or like this, then V would be a complex quantity, and the cancellation will not be total, and a contribution will be there, that is to be treated as the either or as the sink term or the source term in continuity equation. For the present time, at present we assume V to be real, and this term gets cancelled, and here from we get minus H line square upon 2m psi star this part, this bracket has been put to remind us that Laplacian operates only on psi star, not on psi. And on the right hand side I will have H cross psi star del psi del t plus del psi star del t psi, which is equal to IH cross del t operating on rho, where rho is as usual psi star psi. Now we multiply this equation by dV and integrate over the volume V on which the system prevails. So we get this is the result. Recall Green's second identity. We have Gauss's theorem, Gauss's divergence theorem, and this where A is a vector field and V is a volume bounded by a closed surface S. If we take vector A as derived from two scalar function f times grad g, then this becomes and on the right hand side I get on interchanging F and G I get if we subtract one from the other, the result is on the right hand side the gradient of scalar point functions are involved. So this is a vector and this is a vector. This is known as Green's second identity. We can apply this to convert this volume integral into a surface integral. In doing this, I identify F with psi star and G with psi. So the result is psi star or we write this side first. So dV is equal to H cancels with this power, so it is minus H, and this is 2mi times the quantity within the integral sign this we write as in doing this we have introduced a quantity J we have introduced a quantity J called the probability current density, and J is defined as H line by 2 mi psi star this is a vector quantity, and vector quantity in the sense of probability. So if we convert this into a volume integral, then this becomes dV. There are volume integral on either side, so the result is divergence J plus del rho del T is equal to 0. This is the continuity equation that we know in electrostatics or in fluid dynamics. Rho we have defined as the position probability density in that, and you recall this equation in current electricity. In that case, rho was the charge density and J was the current density. Keeping this spirit in mind, this is called the probability current density. Probability current density. Note that psi is a representation of position, then nabla psi is a representation of the momentum. So the knowledge of J, or the probability current density, requires simultaneous knowledge of position and momentum, which is not permitted by the uncertainty principle. So rho can be measured as accurately as we wish, but J cannot be measured with ultimate precision. There is a restriction on the measurement of J, and the restriction is due to the uncertainty principle. J, what is the interpretation of J? If we look at this equation, so this J is actually the particle flux. JDS is the particle flux that is crossing the surface area S, closed surface area S. So this is the total particle flux across a closed surface. So J is a measure of particle flux. How J behaves for the different types of wave that we know, we want to study that, how the form of J changes for different types of wave. So we first write the expression for J, probability current density, is equal to H line by twice Mi psi star grad psi minus. Let us first take plane wave. A plane wave in 3 dimension, we first consider the example, and we know that for a plane wave, the particle flux is the same all over, and it doesn't have any dependence on space and time. So plane wave, we represent the plane wave as a plane wave is defined as a wave, the wave front of which is a plane. That is, this is the if we have a plane whose normal is given by the k vector or k cap vector, then if we consider any point on this plane, then the position vector of any point on this plane have the same projection in this direction. So this is the definition of plane wave. If we operate del x on it, on psi of x, RT, this part is xkx, and so this is I kx times psi. So if we consider all the components of psi, we come across that this is equal to Ik times psi. Similarly, psi operating on let me first know what is psi star of RT. Psi star of RT is obtained by the A star, because A may be a complex quantity as well, and this is e to the power minus I k dot r minus omega t. So if we operate I get minus I k psi star. So if we put all these quantities in this expression, J, probability current density for a plane wave, to remind that it is the result for a plane wave, I have put a suffix P. From this, sorry. Uh, from this part I will have a star e to the power minus I k dot r minus omega t. From this part I will have I k times a e to the power plus I k dot r minus omega t. And from the second part, this there is a minus sign over here and there will be a minus sign over here, so the same thing will appear and we multiply it just by 2, and these two term cancels and a makes it a modulo square. So the result is this I cancels with this, 2 cancels with this, so the result is h line a modulo square by m. If this is being a wave function, then psi star psi is rho is a modulo square, and I have missed k, h line square, k is missing, the k was there. So h line square k is p by m is v. So this is actually rho times rho times the velocity. This is indeed the particle flux that we argued in case of classical physics, that it is the number density multiplied by velocity. And furthermore, you see that since for a plane wave k is a constant, and plane wave can move anywhere from or in anywhere, so k has a specific value, and so this quantity is same all along. That is, a plane wave is an unattenuated wave that we usually know has been reconciled through quantum calculation. Then let's come to the spherical wave. A spherical wave is given by kr minus omega t by r. This is the spherical wave. And its complex conjugate relation is if we operate psi and grad on this, I am for the time being not considering the time part, so it will operate e to the power I omega t is taken common, a to the power a, so this operates on e to the power I k dot r upon r. It will have two parts. When it operates on this, it is I k e to the power I k r by r, and when it operates on this, it is minus e to the power I k r upon r square. So if we take I k e to the power I k r by r common, I get it and combine it with this, so a e to the power I k r minus omega t by r taken common. So from this part I get simply I k, and from this is minus r. This part is psi, and so we write it as ik minus 1 by r psi of rt. And when this operates on psi star, proceeding similarly, we get there is a minus sign, extra minus sign, so this would be ik plus 1 upon r psi star of rt. If we plug this into this, and for spherical wave we use a suffix x s, then I get h line square by h line by 2 mi psi star, then this part psi, and for this part this is a minus sign, so this makes it plus, so this is again ik plus 1 by r psi star psi. This term cancels and these two terms prevail, so we will have, and this is 2i will be cancelled, so h upon m, and there will be ik times psi star psi. One thing I have omitted the vector sign r cap, and there will be a vector sign r cap. So the result ultimately is multiplied by r cap. Psi star psi, as is apparent from this, is 1 by r. Psi star psi, from this equation we know that 1 by r square. So the result is this I gets cancelled because the 2ik and this 2 gets this is k r cap, and this is h cross k by m, the vector sense is along this, and this is a modulus square by r square. This denotes that the vector is directed along the radius vector direction and this part is the velocity, it is the number density, and it is found that the flux decreases as 1 by r square. If we consider a spherical a point source placed in an isotropic medium, then the spherical wave is generates and propagates isotropically in all directions. If we integrate the flux over a sphere of radius r centered at the source, then the total surface integration over this must be a constant quantity, because with passage of time the amount of energy that has been emitted from here, say at certain time, after 1 second it will cross a surface sphere of radius equal to v. After 2 seconds it will cross the surface of a sphere of radius 2v, and this is the same because the same amount of energy is propagating. So the surface integration of this over a sphere of radius r must be independent of r. That is to say, j dot ds for spherical wave, this note that this is r square d omega, where the solid angle times r cap. So this r cap gets cancelled, and the flux, the closed flux, is found to have no dependence on r. Similarly, similar thing can be obtained for cylindrical wave. For a cylindrical wave, if we consider a cylindrical wave of infinite extent, then we have the wave function we use the rho phi z coordinate system. So e to the power I k rho minus omega t by root rho is the wave function, and we proceeding similarly we arrive at one by rho. If we consider cylindrical waves are generated only when identical points charges are distributed along a straight line. And if we consider a cylinder with the line on which the sources are placed as the axis, then what is the for in the case of very long cylinder or long straight line, the end effect can be neglected, and the flux that crosses this is the rho is equal to constant surface, and which is a this surface area is rho d phi dz. And as we go on increasing the rho value, the same energy crosses the cylindrical surface. In that case, this 1 by rho dependence of coming from J is neutralized by this, and so we get J dot ds over a cylinder. This is independent of rho, radial variable, that should be. So we see that the introduction of probability current density facilitates our further calculation involving the particle flux. So that's all for today.